All right. Hi, good afternoon, everyone. I hope you can hear me. Can you hear me?
Good afternoon, sir.
Yeah, good afternoon. And I hope you
Yes.
can also see my screen. All right. So let's get started. It's 2 o'clock. So firstly, I would like to start by saying sorry that I could not take two of the lectures last week because of some other commitments in the department. So as we go along the semester, I will try to catch up, and if required, I may also release some recorded lectures so you can watch it. So as a reminder, I would be uploading all the lecture material so far, whatever we have discussed on Google Classroom, and I will also provide you the link for watching the lectures again. So all the lectures are being recorded. And let's get started by having a small recap of what we saw in the last lecture. So we are talking about water resources systems management. And in the last lecture, so in the last lecture, we saw why we need to plan or manage water resources systems. So I'm going to turn off my camera during the lecture. So we saw why we need to plan and manage water resources, because when you want to plan a new project, you need to consider the needs of not only at this point, but you also need to consider the needs of what could be the water demands for the future. And to manage water resources, we need to come up with a strategy or a mechanism. For example, if we have a reservoir, so for this reservoir, when and how do we operate it? So meaning at what intervals do we need to open the gates of the reservoir, and under what situations can we do this? So we need to come up with a strategy for us operating a reservoir. We saw the definition of a system. So a system is basically where we provide certain inputs and there would be a processing happening and we would get some outputs. So it's similar to a PC. So we have some input and then some processing and output. So we also saw systems analysis. How do we analyze this? For example, if I want to draw water from a reservoir, so I have a reservoir and I would like to draw 10 meter cube per second of discharge for irrigation. And I would like to draw 20 meter cube per second of discharge for hydropower. Then we need to come up with a plan for what should be the reservoir capacity. So here to meet both the demands of irrigation and also hydropower, what should be the reservoir capacity? And we would like to have minimum capacity for the reservoir so that maximum demands can be met. So why do we need to have minimum capacity for a reservoir? So do any of you have any thoughts? Why do we have minimum capacity for a reservoir? So if we have maximum capacity as much as possible for a reservoir, then that is going to cause inundation on the upstream of the dam. So let us say you have a stream, you are looking in plan view, so the flow is from left to right, and you construct a dam, so that creates a pool of water, which is your reservoir. Now, this reservoir area should be minimum so that the impact on the upstream is also minimum. So our strategy here should be to minimize the reservoir capacity. And to achieve this minimum reservoir capacity, the process is called optimization. So here we are optimizing the reservoir capacity. So I know some inputs. So my inputs are how much discharge I want to withdraw from the reservoir. And my output is what should be the reservoir capacity. And so the reservoir capacity should be optimized so that the impacts on the upstream are minimal. Now, how do we do this optimization? So we saw the types of systems analysis in the last lecture. So one is linear programming. Second is nonlinear. And then we have dynamic programming. And we also have simulation. And we also have optimization using calculus. So these are the different types of systems analysis. So these are the different techniques that we are going to use to optimize a process. So in this lecture, we are going to get started on the analysis. So we are going to start with how do we optimize using calculus. So this is the first step we are going to look at. And once we finish how to optimize using calculus, then we are going to look at linear programming. So now let's get started for optimization using calculus. So before we get started on this, let us take an example so that you can relate more to what I'm talking about. So I have an example problem that I'm going to write down here, and we will try to see how do we solve this example using calculus. So I think in the last semester, all of you have gone through irrigation engineering or water resources engineering 1. So in water resources engineering, you might have learned about the command area or the irrigation and different aspects of irrigation in the first unit. So relating to that, I'm going to take an example. So let us say we have 2 crops. So the 2 crops are grown on an area of 200 hectares. So we have 2 crops that are grown on 200 hectares. And the cost of raising them. So let's say the cost of raising crop 1 is 3 rupees per hectare. So this is just an assumed data. So this is not accurate data. So it may not be 3 rupees, but for simplicity, I'm just saying it as 3 units. And similarly, the cost for raising crop 2 is, let us say, 1 rupee per hectare. So we have cost of 3 rupees per hectare for crop 1 and 1 rupee per hectare for crop 2. And the benefit that we are getting from both the crops. So the benefit from crop 1, let us say it is 5 rupees per hectare. And the benefit from crop 2 is 2 rupees per hectare. So we have a total of 200 hectares of area, and the cost of raising crop 1 is 3 rupees, but the benefit that we get is 5 rupees. And the cost of raising crop 2 is 1 rupee, but the benefit that we get is 2 rupees, right? Now let us say if the total amount of money that we have So let us say we have 300 rupees that is available for both crop 1 and crop 2 together. Now to maximize the benefits, what should be the cropping pattern? So this is our problem that we need to solve, and we need to optimize the benefit that we get from the crops crop 1 and crop 2. So here the problem is, let us say if we have 200 hectares. Now what should be the area for crop 1 and what should be the area for crop 2? So these are the two unknowns that we need to find out. And these two unknowns should be such that we get maximum benefit. So here we are optimizing the benefits that we get from the crop. So this is our target. So we need to optimize the benefits that we get from the crops. So I would like to read the problem again for a few seconds before we get into the solution. Okay. So here we are getting started on optimizing using calculus. So this problem, we are going to look at how do we solve using calculus. And even before getting into the solution, let us recap some of the concepts from calculus. And please let me know if you have any problem seeing my screen or hearing me at any moment. Okay, so let us say we have a variable x and we have a function of some form of x, so which is f of x. So we have a variable x and then we have a function which is f of x. Let us say f of x is varying in some way like this. Now in this function, we have maxima and minimum. So which are the maximum values and minimum values. So f of x will be minimum at certain location and f of x would be maximum at a certain location. And here, when we are talking about cropping, our x would be the area of crops and our f of x would be the benefit that we get. So the benefit would be maximum at some location or for some combination of the areas, and the benefit would be minimum for some combination of the areas. So let us say if I have crop 1, out of the total area we have is 200 hectares. And there could be a number of combinations for crop 1 and crop 2 to make up 200 hectares, right? So crop 1 could be 100 and crop 2 could be 100 hectares each. Or crop 1 could be 80 hectares, crop 2 could be 120, or it could be vice versa, 120 and 80. So there could be a number of combinations in which you can grow the crops. but only for a particular combination of crop 1 and crop 2 areas, you would get maximum benefit. So that is what we are trying to find out. And so we need to convert the data that we have into some form of function, which is f of x. So here our variable would be area, and the function f of x would be the benefit that we get. Now, let us say, let us take this point here, where x is at a higher, f of x is at a higher value. And if we take another value to the left, f of x is at a lower value. Now, what we call this is local maxima. And what we call here is local minima. So even though f of x is the lowest point here, it may not be the global lowest value. So if you consider f of x from here until here, from left to right, our point here, the local minima, is not the lowest point for the complete f of x. So the global minima may be here. And the global maximum for f of x would be here. So for any function, we have local minima, local maxima, and global minimum and global maximum. And how do we find minimum and maximum values for a function f of x? So any answers on that? How do you find minimum and maximum for a function? Of course, you have to take the differential of the function x with f of x with respect to x. So once you take the differential, then you would find out whether the function is minima or maxima. Now, there could be two types of functions. So there could be a function which is like a concave function, and there could be a function which is convex. So what is the difference between these two functions? So a concave function might have a global minimum, but it may not have a global maxima, whereas concave will have global maximum, but it may not have global minima. So that is the difference between these two functions. And to get the local minimum and maximum, so if you differentiate the function df of x with respect to x, and if that turns and equate it to 0, whatever the x you get, for example, x equal to x naught, would be your minimum or maximum. For that function f of x. And if you do a differential again, so which is d square f of x by dx square, and if you get this to be more than 0, then what you have is global minima. So if your second differential is more than 0, then you would get global minimum. And if your second differential is less than 0, then you would get global maximum. So this is how you would find out the minimum and maximum of a function, which is f of x. Now, let us look at an example. For example, let us say I have a function f of x, which is x1 square plus x2 square minus 4x1 minus 2x2 plus 5. And I want to find out what is x at which f of x is either minimum or maximum. So I want to find out x such that either f of x is minimum or maximum. So can you solve this example? So here you have two variables, not just one variable. Here you have two variables, x1 and x2. So in this case, what you do is you take a partial differential. So first you differentiate with respect to x and then equate it to 0. Second, you differentiate with respect to x2 and then you equate it to 0. Then you would get what is x1 and x2. So can you solve what is x1 and x2 and let me know what are the values? So you would get x1 as 2 and x2 as 1. So this would be the solution where f of x would be either minimum or maximum. Now, of course, whether is it minimum or maximum, how do we determine that? So that depends on the shape of the function f of x, whether it is concave or convex. And there is also a process to determine whether the function is concave or convex, but we are not going to look at it right now. Now, let us get back to this example. So where we have two crops, x1, and based on the given conditions, we need to frame some functions such as f of x, and we need to optimize that function f of x. So based on the data here, we have the cost of raising crop 1 is 3 rupees, but the benefit that we get is 5 rupees, right? So the net benefit that we get from crop 1 so is 5 minus 3. that is 2 rupees. And the net benefit from crop 2 is 2 minus 1. So that is 1 rupee. Now we have two variables, which is x1, the area of crop 1 that we need to find out, x2, the area of crop 2 that we need to find out. And the benefit that we want to optimize is the net benefit. So the combined benefit from crop 1 and 2 is what we want to optimize. So let us say I want to call this function Z. Now Z equals, so this is 2 rupees per hectare, and this 1 rupee per hectare is what we get as net benefit. Now my function would be 2 times the area of x1 plus 1 times x2. So this is my function. So this is the function that I want to maximize. And for this, there are two conditions that are given. So the two conditions are, the first is we only have limited amount of money, which is 300 rupees. So the money that we can spend on the crops is only 300 rupees together on both the crops. And the total area that we have is only 200 hectares. So these are the two conditions that we need to satisfy. So if you look at the cost of rising crop 1 is 3 rupees per hectare. So 3 times x1, so 3 is the 3 rupees per hectare, multiply with the total area that we have. That would give us the total amount that we are spending on crop 1. Plus on crop 2, we are spending 1 unit or 1 rupee per hectare. And this should be less than or equal to 300 rupees. So this is our constraint. So this is the function that we want to maximize based on a constraint. So we have a constraint or a condition that we need to satisfy when optimizing the function. And for crop 2, again, if we look at the total area, so the total area that we have is 200 hectares. So the total area, which is x1 plus x2, should be less than or equal to 200. So this is our constraint 3 that we need to satisfy, constraint 2. And we also have one more constraint, that both x1 and x2 should be always more than or equal to 0. So the area cannot be negative. So the area has to be always positive. So both x1 and x2 should always be more than or equal to 0. So this is our constraint 3. So here we have one function that we want to optimize, but we have 3 constraints that we need to satisfy when we are trying to optimize the function. So when we are trying to optimize or maximize the function. So we are trying to maximize Z based on the 3 constraints that we are given here. So let us say the function that I want to optimize is f of x. And let us say I have a constraint g of x. So if it is simply an f of x where you do not have any constraints, then you would simply do the differential of f of x with respect to x, and you would get either minimum or maximum. And when you have a constraint, then the procedure is going to be different. when you want to optimize or find minimum and maximum of a function. And the way that we would be doing it is, I'm going to discuss that. So we have a function f of x that needs to be optimized for a given constraint g of x. Now, what we are going to use is Lagrangian. I don't know if you have heard this before. So this is Lagrangian multiplier method. So when you have a function and a constraint, we are going to use Lagrangian multiplier method to find the minimum and maximum. So the Lagrangian of f of x would be f of x minus lambda g of x, where lambda is a Lagrangian multiplier. So we have converted the f of x into a Lagrangian function, Lagrangian of f of x, which is f of x minus lambda g of x. Now, to find the optimum or the minimum and maximum for this function, you take the differential of Lagrangian of f of x, first with respect to x, and equate it to 0. Then you would find what is x. And again, you differentiate the Lagrangian of f of x with respect to lambda and equate it to 0. So you would find a value for lambda. So if you solve for these equations, then you would get what is x1 or what is x, and you would also get what is lambda. Now, whether f of x is concave or convex, this depends on the lambda. So whether f of x is either concave or convex would depend on lambda here, which is the Lagrangian multiplier. So here, what we looked at is, let us say we have a function f of x that is subject to a constraint g of x, right? Now, this could be g of x equals to 0. So let us say it could be x1 plus x2 equals to 0. So this could be our constraint where we have an equality. So g of x equals to 0. So we have a constraint that x1 plus x2 equals to, let us say, 200 exactly. So meaning at any given time, the cropping area or the area on which crops are grown is always 200 hectares. But it need not be 200 hectares to get maximum benefit. So sometimes it could be only 80 plus 80. So it could be 160. So here we have an equality where x1 plus x2 equals to 200. Now, if we do not have that equality in the constraints where so now we are talking about g of x that could be less than or equal to 0, for example. Or what we have in our example here is, so here we have an equality. So 3x1 plus x2 less than or equal to 300. Or if I rewrite this, that becomes 3x1 plus x2 minus 300 less than or equal to 0. So now our g of x is not simply g of x equals to 0. So there is an inequality here. Now, if we have an inequality, how do we solve this, or how do we optimize this? So if we have an inequality where g of x is less than or equal to 0, then we would need to first convert g of x. So let's say g of x is less than or equal to 0. Then we need to convert g of x into an equality constraint. So let's say if I am adding plus s squared, so some constant I am adding to convert this less than or equal to 0 into an equality. So now my constraint has changed from inequality to equality. Or there could be a case where g of x is more than or equal to 0. In this case, what I can do is g of x minus s square equal to 0. So here I have introduced minus s square to convert this into equality. So here we are trying to eliminate inequality in the constraint. Now, once we try to bring in a new constant, which is s or s square, then the process of solving this is iterative. So it is not a straightforward process. We need to do an iterative process. Again, we are going to use the same Lagrangian method, Lagrangian multiplier method. But here we would also need to do some iterations to solve the best combination for S. So this is a bit mathematical in what we are going through this lecture. So I think I would provide you the lecture notes as well as some reading material so that you can also go through this again once you go back to your rooms. So let us take an example where we have a function f of x that we want to optimize. So let us say f of x is a function of x1 square plus x2 square minus 4x1 minus 4x2 plus 8. And the constraints are minus x1 minus 2x2 plus 4 more than or equals to 0. And the other constraint is 2x1 plus x2 less than or equal to 5. So we have a function that we need to optimize subject to two constraints. Now, as I said, here we have two functions, and we want to first eliminate the inequality. To eliminate the inequality, we need to bring in some variable s1 so that this more than or equal to or greater than or equal to 0 becomes equal. So I'm going to rewrite this constraint again. So we have minus x1 minus 2x2 plus 4 more than or equals to 0. Or you could say x1 plus 2x2 minus 4 is less than or equal to 0. So I simply multiply with minus 1. So your more than or greater than or equal to 0 converts into less than or equal to 0. And then I'm going to introduce a new parameter. So now you can see I have eliminated the inequality. So I have made it an equality, so equal to 0. Similarly, the other function is 2x1 plus x2 minus 5 is less than or equal to 0. And so 2x1 plus x2 minus 5 plus s2 square equals to 0. So that is what we did here. So we had an inequality in both the constraints. So now we have removed the inequality. Now, once we remove the inequality, then we apply the Lagrangian multiplier method. So the Lagrangian of f of x would be f of x minus lambda g of x. Now, if it is only one constraint, then we only have one lambda, but here we have two constraints. So I'm going to say lambda 1 g1 of x minus lambda 2 g2 of x. Since we have two constraints, so I'm applying, we have two different parameters, lambda 1 and lambda 2. So using this Lagrangian of f of x, what we would get is the Lagrangian of f of x is minus x1 square minus x2 square plus 4x1 plus 4x2 minus 8. So this is the f of x minus lambda 1 times g1 of x and g2 of x. So g1 is x1 plus 2x2 minus 4 plus s1 square minus lambda 2 of g2 of x. g2 is 2x1 plus x2 minus 5 plus s2 square. So this is our Lagrangian multiplier. Now here we have the variables that we have are x1, x2, lambda 1, lambda 2, and s1, s2. So we have 1, 2, 3, 4, 5, 6 variables. Now, all these 6 variables, we need to first take differential. So we need to take a partial differential of L with respect to x1 first, and then we need to take a partial differential of L with respect to x2, partial differential of L with respect to S1, S2, lambda 1, and lambda 2. So we take the partial differential with respect to all of them. And here, since we are talking about optimizing, meaning we are talking about either minimum or maximum. So all of these would equal to 0. So you subject them to 0 and then find the values. So let us try that. So first I'm differentiating the function Lagrangian with respect to x1. So what do you get for this? Can you solve for this? So if you solve for all the differentials, then you would get a set of equations that need to be solved again. So the solution for this, we are going to discuss in the next class. How do we find the optimum solution for this when you have two or more constraints on a given function? But I would like to know if you are able to follow what I'm teaching today. So are there any questions so far on this? So this is very mathematical. So I'm going to send you the lecture notes as well as some reading material. I highly recommend that you go through all of that so that you understand what I'm teaching you. If you have any questions, please feel free to get in contact. We can discuss further. So if you don't have any questions, then we'll close the class for today and we'll continue the solution tomorrow on how to solve this problem. Any comments on it? So if there are no comments or no questions, then I'll close the class. Thank you all.